Okay, this concept on related rates is actually an extension of implicit differentiation. In applications, it's not unusual for two variables like x and y to be differentiable functions of a third variable, such as time or temperature. In most cases, we're going to use time, but what you have to remember is that x and y are both functions of that external variable. So x is considered to be a function of time, and y is considered to be a function of time, or whatever the external variable represents. So before we get into any applications, let's look at how we would differentiate a function with respect to an outside variable. So let's say we have that x squared plus y squared, or in other words, x and y are related like this. They're related by this equation. So x squared plus y squared equals 49. So therefore, that's how x and y are related. Now, we could take the derivative of each of these terms with respect to that third variable, t. So basically what we would do is we would take the derivative of x squared with respect to t, we would take the derivative of y squared with respect to t, and then we would take the derivative of 49 with respect to t. Now, when we do that, you've got to use the general power rule here, because when you use the general power rule, remember x is a function of t and y is a function of t. So the chain rule is going to kick in. So when you take the derivative of x squared, you're going to have 2x, and then you're going to have to multiply by the derivative of x with respect to t. And the same thing with y squared. The derivative is going to be 2y, and then multiplied by the derivative of y with respect to t. Again, because we're differentiating with respect to a variable other than x or y here, so we have to multiply by the derivative of the inside, and the derivative of the inside would just be the derivative of x with respect to t, and here the derivative of y with respect to t. And the derivative of 49, that one's easy, 0. Well, basically, if you'll notice here, counting the x, the y, the dx over dt, and the dy over dt, it's like there's 4 variables. So if we knew 3 of the 4 variables, we could solve for the 4th. Okay, and notice, basically what this does now is this actually tells me how dx over dt, the rate dx over dt, is related to the rate dy over dt. Thus, related rates. That's where it gets its name. Okay, now this is basically just like the other, but on this example I have 3 variables. So instead of x squared plus y squared equal to a constant, I have x squared plus y squared equal to another variable squared. Well, you do this just like I did over here. The only difference is now that this is a variable, you also have to apply the rule to this one. So these work just like before. 2x, the derivative with respect to t would be 2x times dx dt. This would be 2y times dy dt. And then this would be 2z times dz dt. And again, if we have 6 unknowns here, and if we know 5 of these, we can solve for the 6th one. And notice now, this gives me the relationship between the 3 rates, dx over dt, dy over dt, and dz over dt. So thus, related rates. Suppose we have an area formula for the area of a circle, like a equal pi r squared. Well, we could differentiate this with respect to t. If we take the derivative of a with respect to t, that's what we get, dA over dt. Now if we take the derivative of pi r squared with respect to t, well remember pi is a constant, so we can just kind of think of the pi out of the way for a minute and just take the derivative of r squared. Well, the derivative of r squared with respect to t is what? It's 2r, right? But then remember, r is a function of t, so we have to multiply by the derivative of r with respect to t. So we have 2 pi r times dr over dt. Again, this relates the rate dA over dt with dr over dt. So you could think of this as the rate that the area is changing with respect to time, and this is the rate that the radius is changing with respect to time. And so this equation relates those two rates. Now, what if we have this volume formula, volume equal pi r squared h? Okay, well now here, if I apply d over dt to each, the left side's easy. The derivative of volume with respect to t is just dv over dt. But if I take the derivative of this, I can pull the pi out of the way. So let's pull the pi out front. And then I need to take the derivative of r squared h right here. Well, the derivative of r squared h, since r and h have to both be thought of as functions of t, then I have to use the product rule. So I take the first function, r squared, and multiply it by the derivative of h with respect to t, which is just this. And then I multiply by h, I have h, okay? And then I have to multiply that h by the derivative of r squared. And remember a while ago we said the derivative of r squared was what? 2r times dr over dt. So really it's just 2r times dr over dt times h is the second half. And so now we've related these rates. The volume is changing with respect to time, with the rate the height is changing with respect to time, with the rate the radius is changing with respect to time. Thus, related rates. Now those examples I just went over were really just an intro to kind of get you going on how to differentiate with respect to that outside variable. But in related rates there's a little bit more to it. But here's some guidelines. Make sure you read the problem carefully and think about the given facts together with the unknown quantities. Sketch a picture or diagram and label it. Write down the known facts, expressing the given and unknown rates as derivatives of the variables. Formulate a general equation that relates the variables. So like I did up here, like here I had a general equation that relates the variables. And then differentiate both sides of the equation with respect to t so that you can get a relationship between the rates. And so actually I said that wrong. Up here was the variables related, and then when I differentiated I got the rates related. Okay, and then substitute the values and rates that you know and solve for the question or solve for the answer. Okay, so let's go ahead and start one. Alright, so a circular region expands uniformly at a rate of 0.25 square centimeters per minute. At what rate is the radius changing when the radius reaches 6 centimeters? Okay, so here's the circular region. Okay, here's the radius. Now it's expanding, so it's getting larger, you know, in a circular fashion. Okay, now we know, let me go ahead and start here. We know the relationship between area and radius in this formula is represented by this. Okay, so we'll get to that in a minute. Now, what is known? We know the change in area with respect to time is 0.25. And we know we want to know what rate the radius is changing with respect to time when the radius is 6. Now don't plug the 6 in yet, because you don't plug in the number till last. First thing I got to do is find the related rates. So I need to take the derivative of this with respect to time. Now we already did that before, so you can go back up there and look at it if you need to. So if you take the derivative of this with respect to time, you're going to get d over dt equals 2 pi r dr dt. Well, now I can plug in what I know. I know the area is changing at a rate of 0.25. And we want to know the rate r is changing when r is 6 centimeters. So put in 6 centimeters for r. And then, so I have 6 times 2 pi is 12. So that's going to be 0.25 equals 12 pi dr dt. Well, all I have to do to solve for dr dt is divide 12 into 0.25. Actually, 12 pi into 0.25. So take 0.25 divided by 12 pi, and then that's approximately 0.0066 centimeters per minute. And I know we're talking the radius is changing, so this radius would be growing at a linear rate. So the radius is growing at a rate of 0.0066 centimeters per minute. Okay? Okay, so here's another one. It says, how rapidly will the fluid inside a vertical cylindrical tank of radius 5 feet drop if we pump the fluid out at a rate of 100 cubic inches per second? Well, first of all, we know the volume is decreasing, right? Because we're pumping liquid out. So the rate of volume has to be negative. The rate the volume's changing has to be negative. We want to know the rate, the height would be, like right here. So we want to know the rate the height is changing. So we want to know dH over dt. Okay? Well, the volume of a cylinder is given by this formula. Okay? But we can actually eliminate the R here, because the R is given. Now be careful, because the R is given as 5 feet, but this is given in inches. So we need to convert 5 feet to inches. So 5 feet would be 60 inches. So I'm going to put 60 in this formula for R. So I get pi times 60 squared. So that's 3600 pi times H. So this would be the relationship that I have between volume and height. Okay? And the only reason I could put radius in there is I knew the radius is going to remain constant. So the radius isn't going to change as the water level decreases. The radius is not going to change. Okay, so let's make this straight. Okay, so that's kind of the height of the water level. Okay, so now I can take the derivative of this with respect to time. So the derivative v with respect to time is just it, dv over dt. And the derivative of 3600 pi h, well, 3600 pi is a constant, so that's just going to be 3600 pi times dH over dt. Well, now I can plug in what I know. I know dv over dt is negative 100, so plug that in. And then I know all I have to do to find dH over dt is divide 3600 pi into negative 100. And then so I did that and plugged it into a calculator, and I got about negative 0.0088 inches per second. So the height is actually decreasing at a rate of negative 0.0088 inches per second. And that makes sense, because if the volume of this tank is decreasing, then wouldn't it make sense that this height would be decreasing? So that makes sense. Okay, so on this problem, 2 truck convoys leave a depot. Convoy A is traveling east at 40 miles per hour. So here goes convoy A down here, traveling east at 40 miles per hour. Convoy B is traveling north at 30 miles per hour. Okay, now what I'm going to have to do here is you need to make sure you understand that as one convoy travels north and one travels east, the relationship between them is x squared plus y squared equals z squared, because of the Pythagorean theorem. Now, if I take the derivative with respect to time for each of these, and we did this earlier, I get 2x dx dt plus 2y dy over dt equals 2z over dz dt. Now, this is the relationship between the rates. Now, actually, I know that dx dt is 40. I know that dy dt is 30 because that's the rate they're traveling. And I'm after dz dt, so I need to know the rate the distance is changing between them. Well, at the 6-minute mark, you can determine that at 6 minutes that x is 4, y is 3, and then if you know x is 4 and y is 3, you can use the Pythagorean theorem to find out that z is 5. So we know at the 6-minute mark, those are the 3 values for x, y, and z. And now I can go into this formula and I can plug in the values x is 4, y is 3, z is 5, and for dx dt I plug in 40, for dy dt I plug in 30, and then you take this problem now and solve it for dz dt, and you'll actually get that dz dt is equal 50 miles per hour. So the rate at which they're changing at 6 minutes is actually 50 miles per hour. So I'll do some more of these examples on the next video.